right. We're live. My name is Jeff. We're going to be working on Wanix. I've got a couple people here with me. Rohit is shadowing me. I'm going to say hey.
Hi, people.
And Tara's on here too. Keeping an eye on chat, etc.
Hi.
I'm gonna kind of let it sit here for a minute while I check the stream and share the link a couple of places, and I'll let people come in if anybody comes in. I don't usually have a big viewership, but sometimes if I'm consistent at streaming, I do, but yeah, let me get this link out. We'll do my Discord and Twitter. Okay, I think we're about ready. Yeah, let's get into it. So as a quick introduction, Wanix is a Unix-like development environment that we put together about a year ago, a little over a year ago. You can go to wanix.sh and view this demo. It's very much kind of a proof of concept, a research project, experimental, trying a bunch of stuff. And a big part of the idea was to try and bring in some ideas from Plan 9, but the original sort of demo version didn't have those sort of baked into the core. And so we're starting over from scratch. I sort of figured out how to do that. And so now we're building Wanix again. So it's not going to have all the functionality yet that it did in the demo. But it will be pretty interesting because it's sort of, we're implementing the simplest thing to get the rest of the system, if that makes sense. That we can bootstrap the rest of the system. So we'll kind of start to see that today. The repository is on GitHub, although the active development is happening in the 03 branch. If you want to follow along. And yeah, let's do it. We're using Cursor, which I guess it gave me Cursor Pro trial, and today it said that the Pro trial is over, so I don't know what the difference will be. For the most part, it just feels like it's Copilot, and then also I can ask questions and have it write code, which the other day we had it actually kind of do some work for us, which was kind of cool. Otherwise, it's just VS Code. and kind of annoyingly sometimes will autocomplete things, and sometimes it's correct and sometimes it's wrong. Anyway, so this is kind of the to-do for today. Kind of review what we have in here so far, since it's not entirely from scratch. We did start this the other day, but we'll kind of focus on building an in-memory file system based on the file system abstraction that we have here that we talked about the other day. And we'll build a namespace, or at least refine a namespace implementation that I started that is sort of the core of kind of a big part of the Plan 9 architecture. And then we'll create a file system. So I guess like Plan 9, in Plan 9, almost everything was a file server, in that you did everything through the file system, which meant, you're using, there's fewer concepts, right? Like there's, Linux has hundreds of syscalls. The file system is only, a couple, 40 syscalls or something like that. And in Plan 9, a lot of things that would have their own syscall could just be done through the file system. So you could just do them with those 40 syscalls. So trying to get the most out of what you have is kind of this like design philosophy of Plan 9 and Go and a lot of my work. So the idea is we're building the sort of kernel of Wanix is basically a file system. And then the first file system that we'll make for it is one that lets us manage the file systems and create new file systems and mount them in it. So then the rest of the work is just making file systems. In Plan 9, the idea of if you extended Plan 9 with a file system, you would call it a file system or a file server. Though a lot of stuff, even in Linux and Unix world, on the file system is considered a device. It's actually what /dev is short for device. It's actually not developer or development or anything like that. And on Linux, this is where devices are mounted, like your USB devices, but also hard drives and stuff like that. In Plan 9, there are devices that would actually do stuff like give you your environment, give you your mouse. So if you were to open dev/mouse and then you move the mouse around, you would get the coordinates of the mouse. Stuff like that. Those were sort of devices in that they represented, in some cases, devices, like physical devices. But they were also devices in that they were not data storage on the file system. So a lot of the stuff we're doing with file systems right now doesn't really have to do with storage. Like we're creating almost like APIs or ways to manage resources. The first one being file systems or devices. So one of the things I'm trying, I don't know if I'm going to stick with this, is calling the unit, or like if Wanix had a module system where you could extend it by adding more modules, I'm going to try calling them devices. And what I mean by device is literally just a file system. So these will kind of be interchangeable. But ultimately a device is just a file system that can be used in the Wanix file system. And somehow from that, we're going to get to basically a whole working operating system. But so yeah, namespace and then the device file system, which will kind of look something like this. I sort of sketched it out. This is sort of some of the basic conventions in the Plan 9 style file systems that aren't. And I guess the reason why I like device is because file system definitely, even though technically it's file system makes you think place to store data files. And so we'll see if this kind of helps conceptually make it easier that, a device is a file system that may either be a place to store files, data, or be a quote unquote device, a kind of API to some subsystem. Does that make sense, Rohit?
Yeah, like I got the overall idea what we are trying to do here.
Yeah. So, we were talking about file systems before. Now I'm going to start saying devices. It's the same thing.
Mm-hmm.
And then really quick, some of the conventions from Plan 9 are there's a file in the case where you're managing multiple resources. There's a file called new. And when you read that file, it gives you an identifier to a newly created whatever that is, which is going to have its own directory. And so within this directory, this one is sort of device one. And then in there, we have these files, but they actually are just kind of like fields. Like you could read name and it'll give you the name of the device. You could read type and it'll just be the type of the device. Control is another pattern in Plan 9 where instead of reading this, you write to it. And when you write to it, it's effectively running a command. And so this is an interesting pattern because you don't have to necessarily have commands or executables sort of stored on the file system. The file system can just have these sort of nodes that you would write to, and then they would perform the command. So in Plan 9, they would often call these CTL, short for control. And so we'll kind of continue that pattern here.
Right. It's interesting since I am on Windows and I'm using the WSL extension for Linux.
Mm-hmm.
And I just checked, it has a dev directory, which is, I used to think it was developer, but I just checked in there and it has some of these control things and everything in there. Yeah,
that's it. Actually, I don't know at what point I realized it as well, but yeah, dev is /dev, pretty universal because it goes back to Unix. But so now, Linux and BSDs and, Mac, pretty much everything has /dev. And you can see in here, most of these things like TTY is short for teletype. So these are terminals. Like this session that I'm in, terminal architecture is interesting. I don't really want to get into that. Our disk, these are actually, the disks that are attached to my system. They have some other kind of like random, like this is a /dev/random is very much one of those like dynamic, sort of device resource where when you read it, it's just going to give you a random data. And so certain Linux systems sort of use that as a way. So it sort of almost creates like a runtime, for the system. That's kind of how it was sort of set up. Anyway, so you can look at /dev. Everybody's going to have different stuff in there. But anyway, so we're creating our own, except our version isn't just like a convention where we put devices. It's actually where we manage devices. And in this case, a device is a file system. Like I almost was calling this earlier file system. So it'd be the place where we create instances of file systems. which is kind of true what we're going to be doing, but I'm reframing it as device. So anyway, we'll see if this sticks. And by the end of today, we should be able to dynamically create an in-memory file system. So a file system that actually stores data, but it's only storing it in memory. And we'll sort of create and set that up via the file system using this. So we'll create a new in-memory file system will be registered as a type of device we can create, and then we'll create it. And because we set up the fuse mount stuff, which I'll show in a bit just as a review, we can actually use our command line to create that file system because it's just file system operations. So our little Wanix, this is sort of it's like an embedded operating system. It's not operating system in the sense of a hardware abstraction and, all of that. It's kind of something different, something new and weird, but it kind of is like a file operating system. So, okay, so quick review of kind of what we have in here. The old code was, other than some of these project files from 02, has been cleared out. We did we sort of stubbed out a little Wanix CLI, so we can use this as our sort of tool to do Wanix things. We have one command here called serve, which what we finished the other day was we created an in-memory file system, sort of predefined here with these two files. And then we used a library that lets us work with Fuse, and Fuse is a system for basically extending your system's file system. So this way we're able to take the kind of virtual file system in our Wanix world and actually make it real by sort of mounting it to the file system of your host computer, and then you can interact with it on the command line however you want. You could even open it in Finder and stuff. But anyway, so that's Fuse, and so we then have a system that takes a file system and then mounts it as a Fuse file system. And I guess we could do a build of what we have here. And we're using kind of a framework in a library called Toolkit, which has sort of a framework for building CLI stuff. So we automatically get this usage and help stuff. We could see that there's a serve command. We could do -h, and it kind of gives us help. We haven't defined much help for it, but otherwise we can run serve. And looks like we didn't output anything. We just assumed that it works. So if let's see if it mounted it. Yep. Oh, nope. That didn't seem correct. Actually, using Fuse can be finicky because it can get into a weird state. And see, device not configured. Once you can get into a state where you have this kind of broken path. And I forget how we actually get into that state. I'm gonna, so I don't want to figure that out right now. We'll just create a different one. Obviously, if I restart my computer, it'll go away, but so usually in Linux systems, Unix systems, you create a directory where you're going to create the mount. So there is an empty directory here. And then when we do the mount, it basically kind of replaces it while that mount is running or serving. And then once it stops serving, it goes back to being an empty directory. But this also helps in that it will complain if the directory doesn't exist, because it kind of expects it to exist, I'm pretty sure. So if we run this again, oops, I didn't build. Okay, and now we're getting some logs, so it looks like it does work. If we go to Wanix 2, fortune and hello, which are these two things here. Hello is a file, and fortune is a directory with another directory in it, and then a file. So this file system is basically a read-only file system. And it's actually from the file system test package in the standard library. It's made for when you make sort of implement file system or implement. It's a little confusing because, there's sort of like the real file system of like what we mounted with Fuse, and then there's this conceptual file system, which is what's in our code. And I kind of say file system in both cases, but really a file system in here is just something that implements the file system interface, which then we can use FuseKit or other things to actually mount as a real, quote unquote, real file system. And as I mentioned, we weren't going to use MapFS, we ended up using it here just to kind of get this working. But one of the first things that we're going to do is create our own version of this, because the limitation of this is that it's read-only. You sort of define it when you declare it, and then you can't write to it. For example, we're in this directory, and if I were to do touch, which creates a file, it's going to say permission denied. Yeah, that's the first thing that we're going to do. But I also wanted to really quickly review this file system package that we kind of put together the other day. The idea is that it extends the IOFS standard library package that was added to Go recently. And the reason why we're extending it is because they define a file system in the most minimal way possible. A file system is just something that lets you open a name and get a file or an error. Typically, a file system, a real file system, will have much more than that. You can, make directories, you can delete files, all this stuff. Most of those things are kind of mutable operations. And I think what they were going for with this interface was focusing on the minimal use case, which is a read-only. Because you can still add more methods to something if you implement open. They're just not sort of standard unless they define these interfaces. So for example, they've added they came up with something that I hadn't really seen before in the Go ecosystem, which is interface extensions. So a file system is always just something that has open, but a statfs is something that has open and stat, which will give us file info, the metadata. And so that kind of sets up a pattern that can be used to implement the rest of the methods that you would need for like a real full usable file system. And so what we did was we created a package, and in part of the package, we actually create essentially aliases, and it looks like Rohit, check this out so we can get rid of this to do. We basically create aliases for all of the symbols. So we have all the constants and variables and types. We try and make aliases to the actual IOFS, and then we can add stuff to this package, and then wherever we would normally use IOFS, we can use this instead. And everything, that way we're not working with two different packages like IOFS and then IOFS and then RFS, which would have to have a different name like FSEXT or something like that. So what we've added to this are basically little extensions like this for all the other common methods for working with a file system, as well as these utility helpers. What this does is it makes implementing an API very a progressive thing. So what I mean by that is in third-party file system abstractions for Go. This is a popular one called a Pharaoh. Its interface is defined as this whole thing. So if you want to make a file system, you have to implement all of these methods. Even if it's a read-only file system and it doesn't make sense to be able to change stuff or make directories, you would have to implement those and then, return permission error or something like that. But this new setup lets us, we just have to implement open and then any other number of methods, and then we don't have to implement the ones that we don't want to support. And we'll still kind of adhere to this file system interface. Does that make sense? I wonder why these turned blue. Cool. So that's the file system package. And then we also have this Fuse kit, which is really just a light wrapper around this third-party Fuse library that lets us take a file system and then it sort of converts it to implement all the methods that's needed for Fuse, which is very similar, but just like slightly different. So it's basically an adapter. And so normally if you were to implement a Fuse file system, you'd have to implement all these Fuse methods, get adder, read dir. It also has this kind of progressive API system where you can just implement the methods that you need, and then it'll kind of figure out how to make it work. But it is much more complicated. So by creating this adapter, and since we already have this API for file systems, we can just implement file systems with this API and then mount them as Fuse file systems using this adapter. So that's what Fuse Kit is. And that's the code so far. So let's get started on this in-memory file system. I'm trying to decide whether the package should be memfs or just mem or in mem. There's been previously let's see, what did we call it in here? We called all the file systems. So in the previous version of this package, we would call them fs, so memfs, for example. This previous version is based on kind of an old iteration of our file system extension, which has that problem of needing to implement every method. But something else that kind of came up since then is the fact that there is a mapfs now in the standard library, which turns out to be implemented very kind of elegantly. So that's what we were using here. But like I mentioned, it's read-only since it's made to be designed with the standard library file system abstraction, which is read-only. And just in terms of naming, like it's in this FS test package, like, you know, it doesn't, if you're making something that's not going to be used for testing and you're constantly pulling it out of a package made for tests, it's kind of weird. So I think what we might end up doing, and I'm probably going to just do it right here, is copy this. And we can do this because it is BSD. You know, we're going to make enough changes to it anyway. But just because their implementation is so much simpler than this older implementation that we have. So I don't know. What do you think? Should we call the package mem or memfs? I guess you don't have as much experience yet with Go to know what these conventions are, but what do you feel? What do you... Maybe Tara. Go ahead. Yeah, you can, what's your...
I mean, I would prefer in memfs just to be as clear as possible.
Okay. Tara, do you have any feelings?
I don't know. I don't think so. I feel like you would be better suited, I guess.
The problem is that I don't really know. I guess, you know, Rohit wants in mem, but it's memfs has been used so many times before that I'm just going to keep using that convention. So we'll start changing this stuff. Probably most immediately. This element can't be renamed. Why not? How bizarre. Oh, because it's not maybe a proper package until I declare that. Okay. So this is why I was considering mem, is because in Go, you typically want to avoid redundancies with naming. So if you have a package called mem fs, and then you have fs in it, there's kind of redundant. Like, it's a rule of thumb, like it's okay if you do that, but like the ideal is to try and make it so that it reads as a whole name, memfs. So I don't know. We can always change it. So it'll be redundant for now. For the most part, all this is great. One of the reasons why I like this implementation is because instead of doing the file system as a struct, and then having, you know, a bunch of internal fields for storing the data, it's literally just based on a map. Because in Go, you can declare types like this, and then you kind of declare what its kind or derivation is. So normally it'd be like struct or interface, but it could also be int. It could be any of the built-in types, and you're just more or less creating a, not necessarily a subclass, but just like a derived type. And so in this case, fs is now just, in a way, a shorthand to a map string, how do you say that? A map of strings to files. And the cool thing about this that I like is that you can basically use the syntax of declaring a map. So instead of saying, if it's a struct, you'd have to declare a struct and do new or whatever. But the fact that it's a map means you can just kind of declare in this map syntax. And most of this is implemented. Most of the, I guess the other thing too is that it really only cares about the files. So the fact that this is in a subdirectory is it automatically creates these directories. So as a convenience, when you're trying to declare a file system really quickly for testing purposes, like what this was made for, you don't want to have to bother with like making directories and all this. You can just kind of declare the files that you want in the file system and it figures it out. So yeah, I like this implementation. So we're going to kind of base it off this. They have some helpers because it's made for testing. A file system doesn't need to have glob or readdir or read file or stat or sub. It can, like it's designed so that if you have those, how do I say this? Well, for example, actually, I don't really know. Normally, you could just use the function helpers that are in IOFS, like glob isn't there a glob function? So you'd say glob, give it a file system, and use glob this way. If it implements glob, then it will use that to do the glob. Otherwise, glob has an implementation of glob. Globbing, by the way, is I don't know where it originally came from. It's kind of a Unix-y thing. A lot of these old systems have weird names that just like, they had to name something and they come up with a weird name like slurp or glob. And then it just kind of carries forward because like there's not necessarily a better name for it. It's an abstract thing, but basically glob means basically match against a pattern. And usually it means a pattern that includes asterisks. So you could say, give me all the files in user that are in a directory that have a bin and have an ed file. And this star sort of matches anything there. You could do the same with file extensions and stuff like that. So this is not something that a file system should have to implement every time, but this is set up so that if you do implement that method, you can do it however you want. And then when you call the glob helper, it will call this if it's implemented, or it will implement glob sort of itself. That's kind of one of the benefits of this sort of breaking all of these API methods down into separate interfaces. So anyway, we don't actually need all of these. You can see most of them are just calling their helper anyway. They just added these methods as conveniences since this was made for testing. But now that it's not for testing, we can get rid of these, at least for now, as conveniences. They made some interesting helpers that have to do with some technical things I don't want to explain. Let's see. Ooh. So just as a quick overview of this code, right? We've got our file system type, which is a map of strings to this map file type, and a map file type has the contents as a byte slice, as well as some metadata, the mode, the modified time, and sys for some reason. even though that's usually reserved for like platform specific stuff. But this is a virtual in-memory file system, so I don't know why there would need to be that. These are interesting. This is a weird Go idiom where it is basically asserting that a type implements an interface. In languages like Java or whatever, when you declare a type or a class and you wanted to implement an interface, you would say implements, and you'd have to put that as part of the declaration. And the great thing about Go is that you don't have to declare that a type implements an interface. You just do it, and it will compare it based on the structure of the method signatures. The downside of that is that when you compile, it's not going to be able to check to see whether, this was supposed to implement this interface, but it doesn't actually have all the methods for it. So this is basically a way to assert that that a type implements an interface. So by declaring, so this is kind of interesting to explain. So we're declaring some variables, some package level variables, but we're declaring variables without names. So in a way, we're not actually declaring variables. We're just creating this declaration, and we're doing that so that we can let the compiler check to see if it's valid. And by doing that, it will assert that a file system implements FS, the FS interface. So if this type didn't implement open, then this line will cause the program to not compile, because we're trying to assign an instance of this type to a variable that we're basically throwing away immediately, of type FS, the FS interface. So, does that make sense? If file system doesn't have open, then it's going to be like, you can't assign that to this. And so, in that way, it asserts that this type implements this interface.
So can we do it in a way where we don't have to like type variable underscore in the beginning?
Nope. And that's, in a way, the pros and cons of the Go design philosophy, which is, and in general, there's this trade-off of, hey, yeah, this is a thing that we need to do. We might want to assert that a type implements an interface. Instead of implementing that as a feature, like creating a new syntax to do that, like maybe saying implements up here, or whatever, they'll first see, like, is there a way to do this with what we have? That's really the core of this design philosophy, is by like this aggressive, can you achieve what you want to achieve with what you have? Is there a creative way to do that? Because then you're not creating a new syntax. You're not creating another complexity to the system. You're not actually adding anything. You're just using what's already there in a particular way that achieves the goal. The trade-off, the downside is this becomes cultural knowledge, right? I had to explain it, and I didn't even know about this for a long time until I saw it in some code. But at the same time, asserting that a type implements an interface is kind of an optional thing. It's not even, it's sort of like, if you know that's what you need, I don't know, I feel like you're okay with doing this. So anyway, it's one of those weird trade-offs. But what I appreciate is the fact that they were able to, find a way to do that without actually adding a new feature. And that's kind of the cool thing to appreciate. So, okay. And we can define these types sort of separately from the methods on them. So even though we defined this map file, we're going to go back to this fs type and basically implement open. And I think that's the only method now that we deleted those other ones. Open is the only method on our memory file system. And this is where the logic goes for synthesizing directories. So if you're opening something from the map, basically it goes and sees, given the file that you want to open, is that specified in the map? And if it is, then we can just return this open map file type, which is defined later, with this map file, which implements the file, this file interface, right? Stat read and close. So it's pulling it directly out of the map. But if we asked for something like, in this case, if we asked for fortune or fortune K, those don't have entries in the map. They're part of a path in one of the entries in the map. So the rest of this is just code to sort of go through the map and figure out, are there any entries that this name is sort of a part of that would normally be a directory, like a parent directory. And if it is, or if it's not, it will return an error. And then if it is, then it returns a directory that's sort of quote unquote synthesized. It's not real. We didn't declare it. And it does that with this mapter type, which we'll get to. So map file info is a type that is wrapping the map file. So we can think of map file as the authoritative, like this is where the data is stored, that we're declaring, a file. It's when we declare here, we just say, hey, the data is bytes. So this is kind of like the API for, when we're going to create a file, when we're declaring our file system, these are the fields that we would populate. If we wanted to make this hello file have a different file mode, we would set mode to something else. And that's why these are all exported, because they're made for us to declare. But the file interface and the file info interface are slightly different. Like instead of mode as a field, it needs mode as a method. Because I always forget about file info interface. So this, anytime we do stat or we need to get metadata, we get a file info. And here these things are methods. So they've created sort of a separate type called map file info that wraps map file and also has a name. And then that's what implements the file info interface. In most cases, just pulling it out of this map file type. And this isn't an exported type, but that's okay because the way this is returned is as an FS file. So to the caller, this is an FS file. It doesn't matter that it's some unexported internal type. What's interesting is there's actually another type. They wrap it again. Map file info. Yeah, the actual type that they return is open map file, which then wraps a map file info, which then wraps the file map file type. So there's 3 layers of wrapping going on here. And why do they do this? Well, I guess part of it is file info is one interface, And then the actual file interface, stat, close, and read, is another one. It looks like they implement even more. But yeah, that's, I guess, why they did that. Also, an open file is kind of a stateful thing. When you call read on almost anything that has a read method, like a file, it's going, when you call read the second time, it's going to give you the next bytes. So if I, allocated a 10 byte slice here, and I do a read, and the file's 100 bytes, it'll populate that 10 bytes with the first 10 bytes. Then the second time I call read, with however many bytes, it'll populate it with the next byte. So it needs to keep track of more or less like kind of a cursor. And so that's what this offset is. So they have to manage this offset every time you call read. And then that offset is used to index into the slice of bytes on the file. Does that make sense?
Yeah.
They made a separate type for map directory. And that's because directories have to implement this readdir method, which actually works kind of similar to read in that instead of bytes, you can say, I want, I personally don't know at what API or what system needed this, but you can say, give me the first 3 directories, and it gives you the first 3 directories. And then if there's more directories, you can then call readdir again, give me the next 3 directories. So, you can kind of think of it as like paging or something, but usually when you want to get the directories, you just want to get all of them. But in theory, if you have like a directory with, thousands of entries on older systems, maybe it would make sense to just kind of page through them. So anyway, they have to track an offset to implement that. So that's why they created another struct type here for the offset. So anyway, the end result is an in-memory file system that we can read, but we need to implement, we need to figure out what else we're going to implement. Basically, we want to implement all of these. I guess we don't have to implement remove all because that can be derived, as well as make dir all. Kind of the benefit of this is that some of these can be derived. In fact, I'll make it to do. Implement a derived remove all using remove. And similar to for make dir all. Okay, so I guess we're gonna start writing some code, but we've got cursor, so maybe we'll be able to, look at that. It's sort of auto completing for us already. Sure. Let's see. Yes. So make dir so far is, this map structure is actually designed so that you could specify a, in fact, let's get some tests in here. Let's do some test-driven development. And I'll actually just start by pulling in the tests that they had for theirs. So they have 3 tests. Let's see, this is from FS test. no stat. What's that about? Oh, because they had it before. Now we don't have it. So instead we would call fs stat passing m. See, sometimes this autocomplete that cursor does, it like changes. It'll change the code and I'll be like, oh, okay, so then I don't have to write anything else. But then I cursor off and it's like, no, that was just the suggestion. So getting used to this weird autocomplete nature of cursor and stuff. All right, I guess we can run these tests. And I'm gonna get out of this fuse directory, otherwise this will fail. Go test fs memfs. All right, test pass.
You don't have to build this?
No, tests. I mean, it's in the background building it. You can similarly do go run, and it's sort of like, it feels like you're using an interpreter where you just like give it like a go source file, you know, and it will basically in the background compile it and then run that. So tests work the same way just because it's more convenient. So yeah, these tests, first thing is basically define a simple one, and then it uses this testfs helper to see, do these files exist in this file system? And they do, because the Go authors wrote this code. This test looks like it is letting you specify the file mode, so the file permissions. It's one of those things that feels archaic, but you know, a lot of things back in the day to save both the number of arguments, you know, that you would need to specify, as well as save space in memory. They use bit flags for things. So I know that 666 is the octal for, actually, what is it for? It is the Unix file system sort of standard attributes used for file mode is there's a mode there's a bit mask to specify whether something's a directory. So that's why these have D. And these are, again, the super old archaic kind of thing, but it's what's persisted, so we have to deal with it. The first three of these is the owner's permissions. So the owner of this file can read, write, and execute it. The second is the group. So another Unix thing. Files are usually owned by a user and a group. And so these next three are the permissions for the group. And then the last three are the permissions for anybody else. So that's kind of the semantics of Unix file system permissions are basically who can read, write, and execute, and whether it's for whether those permissions are for the user, the group, or everybody else, as well as specifying what this file mode represents. Is it a directory? And I think there's some other stuff that you can put in there. But anyway, all of that information is condensed into this one number called the file mode. So this is just one of those, probably for people getting into the file system API is probably the most like obnoxious thing, because you have to use it the most, and it's, you know, if you're not used to bit masks, it can be annoying. Anyway, I know by shorthand that 7 is short for all, so read, write, and execute. So 777 is read, write, execute for all three.
Mhm.
Anyway, all this was doing was saying, can we use FS and specify the mode? And then if we walk through and get, file info, what does it give us the right mode? And it turns out they have, there's like a 2-string for the type FS file mode. So if you call string on it, it will produce something that looks like this. Kind of cool. So anyway, they're saying this is what the output should be. And then they check to see if that's what it got. And then this last one is, I guess, just checking that the name in the file info is correct. So basic, using a file system but not writing to it. We're going to implement, or in theory, we have implemented makedir. So previously, you could just define a directory in here, like this. You don't have to let it auto create these. You could have entries for each one so that you can specify what mode, what permissions and stuff. But another thing that you should, in theory, be able to do with this file system is do makedir on it and create directories this way. So that's what we'll test, I guess. We'll do up here. Test makedir. Look at that. It's already kind of doing some of this for us. Let's see, it's importing the wrong FS though. Let's see, where did we? Somewhere. Oh, I guess we haven't imported it yet. So this package is called tractor dev Wanix. So that means so this was what I was saying before, is normally you'd use IOFS and we could just replace that with FS. And it works, and it'll have our extensions. So this isn't really a complete test. I mean, it tests that it works, but it doesn't test that is that file system actually, is that directory actually there. So I guess we could use testfs to check that fortune is there. Yeah, let's run this test. Look at that. It passed. So this should go pretty quickly, especially if AI is helping us. I mean, it knows file system stuff. What's next? Maybe we should do these in order. Open file's a little weird, so I'm skipping it for now. Makedir all, we can derive that. Chmod, let's do chmod. Yep, luckily it is that simple. Just looking up the entry in our map and then setting mode on it. So that's pretty nice. We can write a test pretty quickly for that. Sorry, AI, I don't know that this is good enough. So yeah, this doesn't even make sense. Always check the output of AI. So let's create a hello file that has a particular mode. Yeah, we'll do 6, and then we'll change it to 7s, which again is read, write, execute. I think 6 is just read, write. And so then we should be able to do something like this. So we'll stat hello. And what we want is 777. I guess actually, yeah, thanks. We want it to be a file mode. Mode. And then want got file info mode. Yeah. So for some reason, this chmod did not actually change it so that when we do a stat on it, it'll error. Let's see. Nope, it passed. I love it when, this is why people love test-driven development, because you're like, you implement the test, which defines the success criteria for your implementation, and then as soon as the test pass, you can move on. You don't have to like overthink as much. It helps that AI is here. This is interesting. Chown, short for change owner. Is there a chown info? There's file info. But yeah, they don't have like owners. What did a pharaoh do? Let's see. Huh. That's interesting. How do you get the file owner in Go? Stat. Okay. So I guess, and this makes sense. And this is an example of why there is that sys sort of escape hatch is not all platforms model file systems the same way. For example, in Linux and most Unixes, there is concept of a user owner and a group owner, and it's based on a number because they have like a lookup table where you can change a file where it says, you know, user program is user ID 1 or something like that. But then actually storing in the files, it's actually storing just a number. Plan 9 actually did it differently and stored them as strings, which means you don't have to do that mapping lookup. Anyway, so that's an example of Plan 9 wouldn't let you specify the owner and group owner as a number. It would need to take a string. So because Go's standard interface, standard library is supposed to be cross-platform, it'll model the kind of the common denominator. And then in cases like this, they'll have something that will let you access the underlying data structure, which will, depending on the platform, have something slightly different. Which actually brings up kind of an interesting case here, like how should this work? In a way, this means that our file system abstraction assumes more of a Linux, Unix style ownership model here. But, you know, one benefit of the way we design this is, in theory, we don't have to implement this. It would still work as a file system. We just wouldn't be able to chown anything on it. We wouldn't be able to change the owner.
I mean, I think at the beginning that should be fine.
Yeah.
But you know, first version.
Yeah, exactly. But if we were to ever use this to, I don't know, simulate a Linux file system, we would need this. So yeah, let's try not having chown.
So it has been a little over an hour, just FYI, if we want to take a break.
Take a break? Yeah, let me... yeah, now's probably a good time to take a break. And which means we will probably... we might not get to the device implementation today. I was trying to think if there's a simpler version, but we should at least get these done. Yeah, let's take a break. How long? What's a good break, Tara?
Well, I mean, we did 5 minutes last time.
All right. 5-minute break. And
2:12.
Unlike the last stream, there's actually audio during this title card, so
Nice.
We'll be back in 5. Okay, 1 minute.
I'm ready to go.
We just need Tara. Tara, where are you? I guess we'll give her another minute.
Yeah.
All right. Yeah, we'll start without her. Oops. So I looked ahead. We only need to implement these methods for now on the file system. And then one thing that I almost forgot is that we need to implement we want to implement write on the actual file. So we do that, and then we can on basically when we open
an open file.
Yeah, when we open a file.
Okay. Yeah.
And close reading. Yeah, that's all we need. All right, welcome back. So this would actually go pretty quickly because we don't need to do all of them. We can just do these, and AI will probably do most of these pretty good. Yep, just setting mod time on the entry. I guess what this doesn't do, so I'll do another pass here, but some of the things that we should probably be doing is checking that the name is a valid path name. So that's one thing that we kind of need to be doing in all of these. So this is just checking to see if the syntax is valid. It's not actually checking to see, does this exist? But it does ultimately return that it doesn't exist. But valid path is basically like just kind of normal, making sure that you don't start or end with a slash. Since in other cases that would be valid, but they're trying to normalize. And making sure there aren't any relative paths. So that's just checking the syntax of it. And then this also doesn't have, if we make a directory and the parent directory that you're making it in, if that doesn't exist, we would want to return an error. So I'm just gonna, if Parent directory doesn't exist. Autocomplete AI saying if the name already exists. I guess I don't know that is how it normally works, but let's try it. Let's see. There's a directory called local here. If I do make dir local, file exists. All right, so yeah, we should probably do if it already exists.
But if it already exists, like some of the like OSs, if you try to create with the same name, it creates a new directory, just adds a number on front.
Yeah, though not Unix file systems. Yeah, that seems like maybe a Windows thing, or but that could be done at different levels. Like maybe the shell does that, or you know. But I'm mostly trying to implement rough parity with kind of standard Unix or POSIX, which is more or less how Linux and Unix work. There's make dir all is one that should try, like it wouldn't return an error. If a parent directory didn't exist, it would just create it. Make dir all, I wonder, make dir -p is kind of make dir all in the shell. Yeah, it doesn't care if it already exists. Anyway, but we'll let make dir all kind of be derived. But for the most part, we want to do this for a lot of these. Let's see. Chmod, we want to make sure the name is valid. We're not creating a new thing, so we don't care about the parent directory not existing. But if the name doesn't exist, we need to return an error. And the same with change times. I guess we'll do this. How can we get AI to do this for us? Return error. If the name doesn't exist. Oh, but this is interesting. Because not all names are in our map. Because parent directories are created on the fly. We can't just check the map to see if it's in there. But I guess we can call open.
Will the name include the whole path as well as a string?
It can. Yeah.
If it's a whole path, then it might be stored as a whole path in the map.
Yeah, exactly. Well, where's an example? In this case, the file is in the map, but like Fortune and K are not in the map. But at least the way that this was designed, those should exist, because if you do open, it will create them. So I think for this, instead of looking, we can maybe create a helper method here that uses open to, nope. Let's see, exists. See, and it's like, oh, just check to see if it's in the map, but we can't do that. We want to do open. Or let's see, do we have stat? I guess we could do stat because actually, let me think about this. We have a helper called, I thought we did. Directory exists. So yeah, it would call stat. And we need to make sure that error not exist is returned by open, which I'm pretty sure it does. Yeah, if it doesn't exist. So we should be able to use, we don't even need to create this. We can just use the helper, the utility function. I don't know why it's not completing, but oh, because it's importing IOFS. That's right. Our tests were importing our extended version, but not this one. Okay, now we have exists, bool, error. Something like this. It's not exactly correct. If there is an error, we'll pass the error, and if it doesn't exist, then we return a path error. Although this is being changed times. Yeah, something like that. And then this is different. This one we're checking to see if the parent directory exists. Thanks autocomplete. Yeah, this is a little confusing. I think you would think the error not exist would be associated with the parent directory name, but it might be that the behavior that it actually does might be this. I don't know. But that's subtle. It doesn't actually matter because for the most part, it's just whether there's an error or not and what the message is. So we can just kind of leave it at that. So this is this if it already exists. Oh, so we do need to check if it already exists. All right, first check to see if it already exists. If it exists, if okay. This is where the error exists. Is useful. It already exists, so. And then here's pretty much the same thing, except let me check the parent directory. This is a Go thing because we declared these variables already. It doesn't want us to declare them again, just assign them. It's somewhat unique to Go in terms of most programming languages. And then this
instead of doing this exist so many times, can we just create a helper method which can just do this? We can just use it whenever you want.
Well, for the most part, exists is the helper method, and the reason why we have these is because we have to handle the return. Like, there's no way that we could. Is that true? Especially because of the OK. Because we're processing two things. Like, if we did create some helper and a return to path error, we'd have to still set the op. And we're using them slightly differently. In this case, we're looking for if the file already exists, in which case the error is error exist, whereas in these other ones, it's that it doesn't exist. So for the most part, we've already created a utility to sort of remove this duplication. There's, in a language like, I don't know, JavaScript or whatever, it would feel like you could reduce this quite a bit more. But I think one of the things about using a systems language is just embracing the fact that it'll be a little bit more verbose. But like semantically, like there's not a whole lot going on here. We're calling a function and then doing two conditionals to figure out what we're going to return, which is very specific to this particular method. But yeah, I mean, that's a good eye for like potential ways to avoid duplication. It's definitely, one of the things that you get that you kind of need to learn getting into programming is like trying to find ways to not repeat yourself. But then after a certain point, you start learning where it's okay to repeat yourself. So let's see. Yeah, I think these are good now. I guess we could write, we did tests for chmod and makedir. In theory, we should test these failure cases as well. We'll just do a little bit of that. So this one is, how do we want to do this? Something like this. We'll try and make a directory called hello, and so this should fail. Please stop adding that. And this will fail. So if this error is empty, then we will tfatal expected an error. Let's see, and how would we test? Oops. We could do foo/bar. And this should error as well because there isn't a foo. Or check, we're testing that if the parent directory does not exist. And this is check for fail if a file already exists. And then finally we check for success. It's one of those things where I guess check for success. We'll kind of do something similar here. Really just if the file exists. Check for fail if file does not exist. this is a chmod. Yeah. So in theory, these tests should still pass. Great. And now we know that our coverage actually covers the error cases, which is important for testing. It's too easy to just think, oh, I test the working case, but and we also have change time, so well, let's see if I can write test change times. It's weird. The auto created test, all it's doing is checking for failure if it doesn't exist. Which, okay, that's great. Now check for success. I think that works. Well, okay, so what we should do is also check that if we look up the value, that it's correct. We want, so change times lets you set two things at once, the A time and the M time. Man, access, A is for access, M is for modified. I was going to create some variables for these so that we can confirm them. Since every time you call now, it's a different time. So if we want to check to see that it was set properly, we're just going to check M time, I think. So we want M time. In theory, we can just do this. Mod time. Whoops. Want would be M time. Got. Mod time. And we'll just assume that A time probably works if M time works. So we'll just run these tests to see they pass. This will be easier to see. Okay. Change times. All right, now we have to do create, remove. Create. Sure, let's do remove first. So it's, what is this? It's checking to see if it's a valid path, which is really just checking the name. So we actually have to check to see if it exists. So we can reuse this. And we'll comment it. It should be relatively obvious what we're doing. Error not exist. Okay. Yeah, and then otherwise we just delete from the map. Okay, in the case where you remove a directory that was synthesized, that's an interesting situation. I thought this was going to be easy. We also, unlike remove all, need to fail if there are, if the directories, well, if it is a directory and the directory is not empty, we need to fail. Whereas remove all will remove everything. Let's see. Fail if name is a directory and not empty. Yes, thank you. And was there another case I was thinking of? We also need to handle synthesized directories. Right? Like path is not in the map, but how do we get rid of that? We'd probably have to do like a tombstone thing, because there's no way to, if it's not in the map. Let me think about this, because if we were to try and remove path, it's not in the map, but we also couldn't because it has, kind of by definition here, it has child files. So maybe we don't need to care about synthesized directories. I don't know. I'll put a question mark on that. But otherwise, this could be a task for you to do, Rohit. Yeah, let's make a test for it. Test remove. I guess we would want to check for failure if directory is not empty. Sure, we'll need an actual example that works like that. So this is a test that will not pass right now, I think. And then check for success, I think. Wait, come back. Autocomplete. Give me what you were, yes, check for success. So what the hell did it do? It says remove hello, and then it's checking if foo exists. Oh, I guess that makes sense. Kind of. No. It's checking that foo does exist, but it's not checking that hello does not exist. I guess we could just use fs exists. If there is an error, then return that. And if it does exist, yeah, so that'll be our test. So this, I think, should fail because of this. Yep. So 90 expected error. It's not the best test error thing, but wait a minute. This is check for fail if file does not exist. Oh, this file does exist. Sorry, we need to make another unknown. Okay, 95. Now it's talking about this one. I should probably have a better fatal message. It would have told us. Let's see. File does not exist. no failure for non-existent file. Kind of. Tara, can you think of a better way to phrase? I think that's the only way we could do it. It's like negative. There's no failure for non-existent file. Yeah, I can't think of.
Yeah.
Check for failure if directory is not empty. No failure for non-empty directory. So just making that a little bit more clear so that if you run the tests, you actually don't have to just rely on the number. You can actually kind of look it up. So this is, Rohit, if you wanted to do this before next time, we have a test for you. All you have to do is uncomment this, and then you'll have a test for this one. Yeah. Let me put your name on this. Nope. Okay, good. All right, so we did remove. We need to do rename and create. Yeah, rename first. It auto-completed a comment giving you a to-do. That's funny. Okay, so this is actually pretty good. It's checking both paths to see that they're valid path strings. Although this is kind of, maybe this is fine. Then let's see, rename old path. We only need to check to see if the old path exists. And that's kind of what this does. I don't know why. Oh, the new path, we actually want to check to see that the directory exists, because you can't just move something to a path that doesn't exist. You know, the directory that you're moving it to needs to exist. So we can do this. And fix those. Oops. Error not exist. Yeah, it's not very... Let's see if we... if I make a file... So there's a file that says file, and I move this file to a directory that doesn't exist. Yeah, it just says no such file or directory. It's interesting that this is kind of a limitation of, in a way, the API, that there isn't really a good... There's a couple of operations like this on the file system where it's unclear. No such file or directory. Is it referring to what I'm trying to move, or is it referring to the fact that this directory doesn't exist? It's kind of ambiguous. Oh, well, I guess it's saying the path, the new path, so maybe that is fine. I think otherwise, all it's doing is creating a new map entry based on the old one and then deleting the old path key. So that should be good. Test rename. check for failure if old file does not exist. And then this one is if new file parent directory does not exist. And then check for success. Come on. It's moving hello to Fortune. I don't know why. It's just thinking you've already used that name, so it'll do it. And then we can use testfs because that basically just checks to see if the file is there. So that should be a good test. Okay, that passes. So that's rename. What are we missing? Create, I think. Oh, thanks, man. It's not. Okay, now it's kind of trying. Okay, let's see how it did. Valid path. I don't know if the operation is create, but we'll just, these op names, I don't know if these are standard names or if they can be anything, but the default is probably makes sense to make it whatever the method is. So valid path, and then check to see if it already exists. Error exists. And then otherwise it creates a new map file with a default mode. I don't know how I feel about that. I think that's a reasonable, although devilish, file mode. Mod time now. And then it returns an open map file. I guess it is an open. You create it to open it. So this does make sense. Yeah, create. Test create. We can just have an empty file system. Let's see. What do we want to check? Actually, we should have a file in our test. Check for file if our already exists. Yes, expected. What did we say? Expected error that. This is pretty close. We create a file, but we don't check that we can write to it, which I'm not sure we necessarily need to in this test. So I guess maybe that's it. So that's all of the file system methods that we need to implement on it. But we also need to implement write on file.
we do have, I don't know, maybe you saw like 9 minutes left. So just, I don't know if that's a good stopping point or if you want to dig into it.
We can, after we implement this, we can try to mount it on Fuse to sort of see that that it works there. So I guess we won't get to the namespace stuff, but at least we'll have kind of made a working in-memory file system. But I need to actually implement write, because how would this work? Write also has an offset. So is it a separate offset? Now I will look at the old implementation that we had here. File. Right. Okay, so at looks like it's offset for writing. Where is that? Is that used for both reading and writing? Yeah, it uses at for both. I don't know if that's how it should work, but so in theory we can use offset. It's also interesting that they're doing this atomically, so it's more thread safe. So current F file data. I don't know what it's doing. File data is a separate thing. So we have file data. You can see how, we've been working with this map FS implementation, and here they organize things and name things fairly different and structure things different. A lot of these things are things that I've implemented, like re-implemented multiple times. Every time it's slightly different, hopefully better. But in a lot of cases, it doesn't actually matter. Data. So then where is write? So the diff between where we're currently at. Oh, and the I see. The end of the file. Okay. Yeah, this gets into some of the weird bookkeeping specifics of the read-write API, which is kind of neat. We'll just kind of copy all of this in and we'll modify it to work with our stuff. So we don't track if closed has happened, which is probably something that we should do. Because you don't want to perform writes after it's been closed. And it looks like they have this whole locking thing. I guess we'll start with just is closed. The music. Let's see. I don't know if we have to implement some of these other things. I'm just gonna comment this out and have it return nil, and we'll just test it against this. So in theory, you can write it to a file, but it won't actually write. But we can at least see that all this other stuff worked. So this memfs, we'll now change this to and all of this should be good. So we'll build it. Oops, build the command and then run Wanix. Oh no. I'm not cleaning it up or something. I'm not sure why. I have to look at some other projects to see what I'm missing here, but Wanix 3 build. All right, we should be able to. The problem is we can create a file, but we can't put anything in it because we can't write to a file, obviously. But that's basically what touch does, is it creates a file without writing anything to it. So let's see. Oh no, permission denied, why? Actually, you know what the problem here is that I'm pretty sure that my fuse kit adapter is also read-only, so we would be able to test this even if it worked. So let's see, what could we test? Maybe remove. Let's try testing remove. I don't know if I implemented it, but override. I did not expect that. Oh, is it like a permissions thing? I think it's because Fuse doesn't have it. I'm pretty sure I just implemented the minimal thing. So, okay, that's something I'm going to do, which is make Fuse kit read write. Read write Fuse kit adapter. So that's it. I guess, we'll just have to be happy that our tests pass. But normally that's not enough, because obviously it doesn't work. But yeah, it feels like a good place to stop. And we'll keep going next stream. Maybe Friday? We scheduled something for Friday, right? Tara? I don't remember.
We did, yes. Let me...
Oh, but that was in the morning.
11 to 1, and then potentially we'll have a call with the contractor.
Okay. Well, we'll figure out. We'll schedule this next one. What the hell is this? Update cursor? No. But I guess that's it for today.
Cool. Great work.
Any remarks, Rohit? What did you learn?
I learned a lot about Go.
Yeah.
It was interesting to see, and I really liked the part when we actually started working on the in-memory file system.
Yeah.
To see how it builds up, and I could actually then understand how actually files are working from the back part.
Yeah.
How the myth. I thought it would be a lot more, but a lot more complicated, but it doesn't seem that complicated. Or maybe they...
No, well, yeah, that's a good point. And actually, part of that is design. If you design a system, like they talk about this with data structures, if you have the right data structure, your algorithm can be very simple. And that's generally true in that, like, if you have a good design, your implementation is very simple. But yeah, it's interesting. Mostly because we're working with in-memory stuff, and yeah, there is definitely a version of this where it would be more complicated. But
okay, or maybe it's just the beginning. It's just like a version 1. So
yeah, I'm sure there's
like
edge cases and stuff that I didn't, check for.
Oh yeah, definitely.
Things like that. Yeah. So we'll see as we use this. All right.
But yeah, it's like the walkthrough was pretty helpful. Like going through everything, how in-mem file system works,
and writing
especially
tests.
when creating a test.
Yeah,
writing tests, that was pretty good.
Yeah. Cool. Well, we'll be back, if not this week, next week. So let's raid Old Timey Computer Show. And that's a Twitch thing for you guys, Rohit and Tara.
Yeah.
You guys could say bye, though.
Bye-bye.
Bye. Thanks for this.
Cool. Oops. That is... All right. If anybody's around, bye.